In the last lesson, we looked at proportions, and now we're going to look at averages or means, and you'll learn that the ends justify the means. That has to do with sample size, and that'll make more sense in a little bit. So let's go ahead and look back. We actually kind of looked at this before. For quantitative data, we typically use a mean value to describe the population. Now we're going to examine the center, shape, and variability of the sampling distribution means. So first of all, our population here is normally distributed. And I'm looking at the mean samples that I would get for a sample size of 2, of 10, and of 25. So you remember we actually did that dropping samples in the first lesson in this unit. Well, if I were to compare the centers for all three distributions of means are the same. And all three look approximately normal, like the parent distribution. The variability decreases in the same way as for proportion distributions. In other words, it decreases in relationship to square root of n. That's not obvious yet, but we'll get to it in a little bit. But what if I look at a different distribution, say a uniform distribution? Would I expect the means to be normally distributed then? So what I'm doing is I'm drawing samples. Here's sample size 5. And I keep adding to it. And then I'll eventually here get quite a few more samples. So you can see there's 5 and there's the mean. Another 5 and there's the mean. And then another 5 and take the mean. So that creates a blue dot. Well, we can keep doing this, or we can actually speed it up here in just a sec and get a bunch more samples. And here's 10,000 and 100,000. So once you start taking a lot of samples, you see that the shape is actually, whoops, sorry, didn't mean to do that, is actually pretty normally distributed. What if I'm taking with a sample size 25? So it takes a little while because I'm collecting 25 data points, then averaging them, and that gives me a blue dot. What you're probably going to notice is that the spread's going to be a lot smaller because it's a lot harder to get a mean, have all your samples be on this end of the curve and have a mean that's smaller. So your spread's going to decrease with the square root of n. Okay? So even for a uniform distribution, the means are approximately normally distributed. The variance still decreases with increasing sample size. So if I fill in your sketches in your notes, that's what I would draw right there for this roughly normal distribution. But what if I gave you a really crazy distribution where it's pretty extreme? I could easily have means over here and here. So let's go ahead and take a look at what that looks like. So first of all, I'm just going to do sample sizes of 2. And it's not impossible to get 2 on the high end, or 2 on the low end, or 2 in the 1 on each end, or maybe even 1 in the middle. But you can see I tend to get one or the other. I get 2 here, 2 here, or 2 here. And this leads to this crazy distribution. Oops. All right. What if I go with a larger sample size? Here I'm using a sample size of 5. And it's still pretty crazy because I can still get really extreme values. But what if I go to larger samples, the sample size 25? All right. I'm sorry, these are sample size 10. So now it's starting to look a little more like what you've seen before. It's kind of normal. Now we're doing sample sizes of 25. See how I gathered 25 data points, added them up, and then put the average here. And when you take a lot of samples there, you can see it actually looks very much like the normal. So you would go ahead and fill in these sketches on your notes. And you can see for what values of n were we able to get an approximately normal sampling distribution for every distribution, whether it was really crazy like this or this. Well, once we got up to about 25, we had a very nice value. But in reality, we're going to use a slightly more conservative value of 30. But we were able to demonstrate it with 25. All right, so when sampling distributions were large enough, we could say that they are approximately normal. Okay, Then we can use our knowledge of combining random variables. We can calculate the average and standard deviation for a sampling distribution. So what is the average of the means? Well, it's just going to be all the means added up by how many I take, or pretty much just the mean for the population. So what about the standard deviation? Well, I'm going to go ahead and add the variance. Now remember that we are actually dividing by n because we're dealing with averages. So I'm going to take each standard deviation and divide by n for each of my variables. Remember, you can division on a standard deviation, that applies. So I'm going to end up dividing them by n, but I have to square them and add them up, right? And to get the standard deviation, I take the square root of the variance. And I can go ahead and get a common denominator here because I'm going to get sigma squared from that one plus that sigma squared, and I have an n squared here. If all the standard deviations are roughly the same, which we're assuming, then I can just say, hey, there are n of these sigma squareds on top, and then that simplifies to sigma squared over n. Well, the square root of sigma squared is just sigma, and just write that as square root of n. So the standard deviation for sample means, like we saw before, goes down by the square root of n. So the larger the sample size we have, the less spread we have. So the central limit theorem is when n is sufficiently large, that is, in our case, n is greater than or equal to 30, the theorem tells us that the distribution for means is approximately normal, even if the distribution of the population is skewed. So if we have a big enough sample, we don't care what the population looks like. The x-bar for the sampling distribution, or the average, is the same as the mean for the population. The standard error, or deviation, depending how we work with this, that's a hint of the future, of the mean distribution is about square root of n times smaller than the population standard deviation. And the reason is it's harder to get on the extremes when you're averaging from your sample. Probabilities for sample means are calculated in the same way, except you have a smaller standard deviation for the mean of the sample. So some of the conditions. You need to meet the normal large sample condition. Either the parent population is normal, and it doesn't really matter how big your sample is, or your sample's large enough. In other words, it's greater than or equal to 30. And then we can invoke the central limit theorem, sometimes called CLT. If it's less than 30, it's really important that you graph your sample data and make sure there is no strong skew and no outliers. Again, that's for samples of less than 30 only. Now, we need independence to make sure that the probabilities are the same for each trial. And usually this is called the random condition because we get it through good randomization. If we're going to combine variables, we need to make sure that our estimate of the standard deviation is usable, and that works as long as we met the 10% condition. Now, sometimes you'll have to state that it is reasonable to assume one of these conditions, that they're met, if it is actually reasonable. Most times when you get a free response question on the either on one of my tests or the AP test, you're going to end up going through all the work of doing the inference, and you might just have to say, well, let's assume that this is true, or it's reasonable to assume that it's true, okay? And then go ahead and show the work. That's usually it. Now, if we ask if the conditions are met, we're not asking you to do a whole big problem. In those cases, maybe the conditions aren't met, so double check them. All right, let's go ahead and take a look at an example. In 2017, the mean math SAT score was 527 with a standard deviation of 107. Since the SAT is standardized and the graph at right is fairly symmetric and mound-shaped, it is reasonable to assume that the population of SAT scores is approximately normal. So we're not doing samples, we're just looking at SAT scores. So there's the mean, and I can just keep adding the standard deviations there. And that would be your model, okay, for individual scores. What is the probability that an individual student scores over 600 on the SAT? Well, that shouldn't be too unlikely. Let's go ahead and calculate the z-score 600 minus 527, which is the mean, divided by the standard deviation, gives us a z-score of 0.682. Okay, and we want to be on the over side, so we're roughly there on the curve. So I want the probability that z is greater than 0.682, so I can do normal CDF, where my z low is 0.682 and my z high is infinity. And basically that gives me 0.248. By the way, there is a shortcut on your calculators. If you specify the original mean and standard deviation right here, you can actually get through. It'll do it straight without doing a z-score. But I strongly recommend you show z-scores and you show curves so that you show that you know what you're doing. Now you'll notice here on this example, I actually put in like 100,000 as my high. It's very hard to enter infinity in your calculator, so sometimes you're just entering a very large number. Make sure the number is very far away from what you're looking at. So if I had entered 1,000, 1,000's not that far away from 600, but 100,000 is very far away. So we take a random sample of 20 students now and record their scores. Can we use a normal distribution even though our sample size is less than 30, which is the central limit there? Well, yeah, because the population is approximately normal, we're fine. So what would the mean be? It's going to be the same. It's 527. But the standard deviation is going to be smaller by the square root of n, or in this case, square root of 20, which is 23.9. So it jumps down from 107 to 23.9. Our averages are a lot tighter. So if I were to draw the model, the mean's still in the same place, but now I'm not going as far. You don't even see 600 on this graph. So the mean scores for the middle 95% of samples is 2 standard deviations away, and that would be 479.2 to roughly 574.8. You might say roughly 479 to 575. Okay, what is the probability that the average score for our sample is over 600? Well, there's 527 and there's 600. It's actually more than 3 standard deviations away. So we want to be on that side. Let's find the z-score. It's 3.05. It's slightly more than 3 standard deviations away. So my z-low is 3.05. My upper is infinity. And so I would go from 3.05 to infinity, and I get less than 1%, about 0.11% probability. Now I could have also entered this in using the mean of 527 and my new standard deviation of 23.9, and that would also give me the same value. So let's go ahead and look at mean birth weights. At birth, babies average 7.8 pounds with a standard deviation of 2.1 pounds. A random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water shows a mean birth weight of only 7.2 pounds. Is that unusually low? So we're looking at 34 babies. The mean is 7.2. Now the population mean is 7.8, but my sample mean is 7.2. So there's my mean and my standard deviation, and there's what I'm trying to find. I'm going to go ahead and find the z-score, 7.2 minus 7.8 divided by 0.360, and I have a z-score of negative 1.67, which you're probably thinking, well, that's not that far away, and you're pretty close. You're right. If I actually put in negative infinity, because we're looking lower, so we're starting way over here, to negative 1.67, I get 0.0475. Well, okay, so it's less than 5% of the time, so that tends to be our marker. It does seem a little on the low side, so it does seem unusually low. So sampling distributions for the difference of 2 means. Sometimes we want to compare quantitative values for 2 populations. A lot of times we want to do that. So we're going to go ahead and use what we studied with random variables and how we could combine them if they were approximately normally distributed. So if both samples meet the 10% condition and the large counts condition, we can use the following rules to combine them. Remember, when I'm doing means, it behaves like the equation. Mean of x1 plus or minus mean of x2 plus or minus, etc. Mean of x to the n. And that should really have a minus sign. Variances add. They do not minus. And so I would add the variance for each one. But remember that variance is standard deviation squared. So I would take the square root of the sum of the standard deviation squared. Again, remember, variances always add. So if I was just looking at the difference of two means, let's get a little more specific. I would basically say, oh, it's just going to be mean for 1 and minus mean for 2, and it's straightforward. The variances, because I can have this formula, there it is for sample 1 and for sample 2, and when you square them, you get that. And then to get the standard deviation, we're just going to square root this, and there's your formula. The standard deviation of the differences is the standard deviation for your first population squared divided by the sample size, plus standard deviation for the second population squared divided by the sample size, take the square root. So what about conditions when looking at differences? We have to meet the same conditions for each individual sample. So we have the random condition that the data come from 2 independent samples or from 2 groups in a randomized experiment. We still have the 10% condition when sampling without replacement, which is almost always. Then we need the N1, sample 1 is less than 10% of population 1, and sample 2 is less than 10% of population 2, if there is no replacement. Sometimes you can actually have trials and experiments where you can keep trying and there's no real limit on the population. So we also have the normal large sample condition for each sample group. The parent population is either approximately normal, in which case you're done. You're like, oh, if the parent's normal, then the averages are normal. Or the sample size is large enough that it's at least 30 so that the averages are normal, even if the parent is not normally distributed. If it's less than 30, and we're not sure if the parent population is normally distributed, we can actually graph the sample data. And as long as there is no strong skew or no outliers, both have to be satisfied, then we can say, okay, we're fine. So we've got another example here. In 2017 and 2018, 605 and 613 Round Rock ISD students, respectively, took the AP Statistics exam, and average scores increased from 3.50 to 3.56. So they actually have the parameters there for the AP scores. They were curious if there was an increase in SAT scores for this group, so they took a random sample of 50 stat students from each year. The average score in the samples for 2017 and 2018 were 1104 and 1125, respectively. The standard deviation in SAT scores were 215 and 211 for 2017 and 2018, respectively. So first of all, what is the shape of the sampling distribution for the difference in SAT scores? Don't let the AP statistics exam distract you. That's just saying, hey, stat scores went up. I wonder if these were just smarter kids and they had better SAT, or maybe the school just got better in both. Who knows? All right. So we're going to say that the distribution of the difference is normal because each sample is randomly obtained and is large. It's greater than 30, so we can invoke the central limit theorem. Now we're going to find and interpret the mean of the sampling distribution. So we just take the difference, 1125 minus 1104. We would say the mean scores increased from 2017 to 2018 by an average of 21 points. All right, and now let's go ahead and calculate and interpret the standard deviation for the sampling distribution, and we need to verify the 10% condition. So I'm just going to go ahead and use the formula we taught you, which is we take the standard deviation for each sample, square it, and divide by the sample size, and then add it together and take the square root. So we have 211 squared, which is from 2018, and divided by 50. Both sample sizes are the same. And 215 for 2017 squared divided by 50, and I get 42.6. So you can see the standard deviation for the averages is quite a bit smaller than the standard deviation for the populations. Well, the difference, the way I would interpret that 42.6 is I'd say the difference in points gained in the sample mean scores for 2018 and 2017 typically varies about 42.6 points from the true mean of 21 points. And I'm not sure if it's real clear, but I'm really talking about the difference in scores. I kind of say it there, so we might be good. All right, and then I still have to check the 10% condition. So 50 is definitely less than 10% of 605, and it's also less than 10% of 613 for both years, respectively. So we're good there. Finally, the really fun part is estimating probabilities. So we're going to estimate the probability based on the samples that there actually was no real difference in the SAT scores for Round Rock ISD AP Stat students from 2017 to 2018. So we're going to assume 2018 is higher, no actual difference. We're going to say anything 0 and lower. So we're going to find the probability of that. So the average difference we estimate at 21. Our standard deviation for these samples is 42.6. The probability we're looking for is a difference of 0 or lower, okay? Or more negative if you want to say. So we use our formula for z-scores, z equals 0 minus 21 over 42.6, and we get a z-score of negative 0.493. If I draw my normal distribution, that's roughly there. It's actually a pretty big chunk of the curve. And when I put it into normal CDF, with my lower z as negative infinity and my upper as negative 0.493, the probability is actually quite high, of 0.311 or 31% probability that there was no actual difference in SAT scores.